Okay, if you haven't submitted your homework through email, make sure to do so before the class or right now. And probably what I'm going to do for the next homework is to put everything on Blackboard. As I see, a lot of people submitted their homework online through email, and I assume most of you don't have any problem submitting their homework online, so we're going to move everything online. Something I think I have to remind you is that please, if you submit your homework through email, please submit a PDF file. Okay. And on Blackboard, you will only get one upload link, essentially, which means that you have to submit a PDF file. Okay. Is there any questions? Yes.
So today you want the physical one to
Yeah, let's do the physical one today. If you want to submit the physical one right now, from the next homework, I'm going to do only the Blackboard one. If you haven't submitted your homework, if you haven't emailed it to me, make sure to submit your homework right away. You can put it here or wherever. This is not mine, but just here.
Yeah, I'll just fold that.
Yeah.
I have a stapler.
Oh, thank you.
Okay, so let's continue the discussion. Hopefully, we're going to finish chapter 2 today, fluid statics, and we are going to solve some example problems on Monday, on Tuesday. For whatever reason, I think this class is on Mondays and Wednesdays. But yeah, on Tuesday, we are going to solve some example problems, and I will post your homework too on Tuesday. You will have a week to submit the homework. You know the deal at this point. The last thing we talked about, let me actually ask you this before I start the lecture. How was the homework? So. Good. We have one. So easy, medium, hard. Who goes for easy? No one. Medium. Okay. That's good. That's good. Medium was the goal. Okay, so we're going to keep the level of questions at the medium level for the rest of the homework. That's the goal. Okay. So the last thing we talked about was the hydrostatic force on a plane surface. And the idea with the hydrostatic force on a plane surface was that your pressure, you will have a pressure distribution as you change the height of your, as you go deeper inside the fluid. Let's say this is a container that contains water or whatever kind of liquid. Your pressure distribution of one of the side walls will look something like this. And the idea was we can replace this distribution with just one force, F. Okay. And we were able to find that force in the previous lecture. We called it FR. FR was your gamma multiplied by the centroid depth, if you will. This is the distance from the center of coordinate system to the centroid, y of c, and then multiplied by the area that is covered by this fluid. So this is the area that is this area, right? This will be your resultant force. But where should we place this force? We cannot place it on the centroid. We actually have to find the location we have to place it on. How should we find that location? We have to write a momentum balance on the wall. So sigma m, a moment balance on the wall. Sigma m has to be equal to 0. We have two forces here. One is this resultant force that we want to find a location for, and this pressure distribution. The moment this resultant force makes is Fr multiplied by a y. And for the rest of it, you just have to take the integral with respect to m. So the moment this F makes is going to be Fr multiplied by a y. And for the rest of it, you're going to have the integral of P. Or instead of P, we can just say a small element of force multiplied by your area divided by your area. And this is gamma. So gamma dF. I'm sorry. So a small, let me explain this. We are trying to find a location that this one vector, one resultant force vector, is the location that this force is being exerted on. At a specific point, right? The idea is this is not the centroid, or we have to find a location. We don't know whether it is a centroid or not, right? So we write a moment balance. The moment this force creates is going to be Fr multiplied by y, which is the distance this F has from coordinate. And the rest of it is going to be the moment all of these pressure distributions, these small point forces, are going to create at that location, right? Which is y multiplied by dF, the small force each of these pressures are creating, multiplied by the y. Is this clear? So the moment that is being created as being applied on the wall by the pressure distribution has to be equal by the moment that is being applied to the wall by this resultant force. Okay? So if you do the analysis, if you keep going forward with this, we already know that your Fr is going to be gamma yc a. Or in the more general terms, if your surface is inclined, it's not a horizontal surface, we have to actually multiply this gamma of c, y of c, by sine of theta, right? This is a more general term. More general term was the thing we talked about in the previous lecture. So you plug that in, Fr multiplied by y of r is equals to integral of y df, right? Okay. So we can replace f here with this formula, and to find this df, we have to take the derivative of this formula, gamma of y of c sine of theta multiplied by A. I forgot the extra exit. Y of C, gamma, and sine of theta are all constant, so they come out of the derivative. The only thing that really we don't really know anything about at this point is going to be the element of area. So we're going to have gamma yc sine of theta A multiplied by y of r, which is that this y of r is the location at which your force is being exerted on, your force F. This is equals to gamma y of c sine of theta integral of y dA. Actually, this y has to remain inside. So this is y multiplied by y, which is y squared dA. Okay. So this location, I'm going to continue this here. Y of r, the sine and gamma will cancel out. Okay, and we take y of c, which is the centroid location, and A to the other side. That's the total area of your wall. We're going to get the integral of y squared dA over y of c A. Okay, again, we have to have a moment balance. Moment due to this pressure distribution is going to be integral of y df. What is this y? Let's say this is your pressure distribution on the wall. This y is the distance from this df, right? That's this df, right? So a small element, the force that is being applied on a very small element of area, right? dA. And then to find the total force, total moment by this pressure distribution, you just have to take the integral from 0 to h. Is this clear? This one, just multiply the force by the r. Then we replace it with this equation. We plug everything in. You'll get to this formula. So this is the location where that single force you are trying to replace the pressure distribution with is being applied on. What does this remind you of, this integral? This is the second moment of area or moment of inertia that you probably have seen in your statics and solids. So this is I of x. So we can actually find the location we are looking for, the point we are looking for, by finding the first moment of area, which is the standardized location, right? Integral of y dA. The second moment of area or moment of inertia, and having the area of the wall itself. So first moment of area, second moment of area, and all of this. I'm pretty sure you remember from your solid that all of these are actually going to be given to you and you don't need to calculate any of that moment of inertia, at least in this course. But there are some people who have already done this for you, done the calculation for you, that have to refer back to that calculation. We're going to see some examples of those calculations here. I have it here. I'm going to put it on the wall. And that's actually that I of x Does anybody remember the parallel axis theorem from your statics for the moment of inertia? Okay, we're going to forget about the derivations here then, because I don't want to go into that detail. So the location, eventually, if you play with that, because the calculation of that I of x is going to be a little harder, so we're going to calculate the I of x as spheroid around the spheroid, right? Over YCA, and based on the parallel axis theorem, which is also mentioned in this book, this is a theorem you have seen in your statics, that's for sure. Yeah, based on this, you can calculate the location as a function of moment of inertia around the spheroid, second moment of area around the spheroid, first moment of area, which is going to give you the spheroid, the area itself, plus that location of that first moment of area, the spheroid's location. That is going to be for the y component of the location. For the x component of location, we can do the same analysis. You get this formula. It's going to be Ixy of c divided by y of c divided by a plus the first moment of area in the x direction. Okay, so this is the point where, again, just to reiterate, okay? We have a pressure distribution on the wall. We want to replace this pressure distribution with just one single force. So we want to replace a distributed load with a single load. That force is going to be Fr. We have the equation for it, right? Gamma y of c sine of theta a, and the location this force is being exerted on is going to be x of r and y of r. So three main equations. That is going to help us replace a distributed load by a point load. Okay. And let me see if I have the values here. I just want to show you that we have these values in the notes. You don't really need to calculate them. Is there any questions so far? So we are clear on what we have done. We want to replace this distributed load with a single force, right? And we had to find the location this force is being exerted on, right? Why does it take so much? It's a very slow system. Okay. So we don't need to, the idea here is that you don't need to memorize any of this. As you can see, if your wall is a rectangular wall, we have the area, we have I of x, we have I of xy, we have I of x, I of xc, I of xyc, you have all of those things, right, for different shapes. So if your wall was any of these shapes, you just come here, get these values, and just like plug them here, get the location you need, and you should be good to go. Is there any questions so far? So let's start an example. Let me mute the image. Let's have an example. This is the shape we are looking at. So we have this wall that has a very small gate here. And this gate has a stop, right? So this gate is being stopped from rotating in this direction. Okay. You have the angle theta, 60 degrees, which is going to be the center of your coordinate system. This depth here is 10 meters. The length of this plate is this door is 4 meters. We are also given the location of the centroid. From the coordinate system. So we are also given the y of c, which is 10 meters. And we could have calculated that, of course, divided by sine of 60. What else do we have? Okay. So the text of the problem is telling us the 4-meter diameter circular gate that you can see here, this gate, is located in the inclined wall of a large reservoir containing water. We are given the gamma of water, which is 9.8 kilonewtons per cubic meter. You always have to keep in mind this gamma is rho of water multiplied by the gravitational acceleration. Usually assume rho of water is 1,000 and is multiplied by 9.8, which is the gravitational acceleration. So 9.8 kilonewtons per cubic meter. Okay. The gate is mounted on a shaft. The shaft is in the middle here. The water that we have. We want to find the magnitude and location of the resultant force exerted on the gate by the water. So force, the resultant force exerted on the gate by the water, and also the location of that force. Okay, what should we do? I'm going to give you 2 or 3 minutes to think about this. But you essentially have all the equations you need. And it's a circular gate. So your moment is going to be, let me unmute the image here. It's a circular gate. So your moment is going to be I x sub c is going to, I don't know if you see this or not. I'm pretty sure you know how to calculate the area. This is I x sub c, pi 4 squared, r 4 r, pi r to the 4th over 4, and I x y of c is 0. Okay. Just think about it, work on this, try to figure it out yourself, and then we will solve this. Okay, do we have any volunteers? It's a pretty easy example. I'm pretty sure you should be able to figure it out. No. Okay. So we have the formula here. FR is gamma YC sine of theta, or we can actually do H of C as well. The resultant force, gamma YC sine of theta. The YC sine of theta here is 10 meters, right? And just plug this value in as well. The signs will cancel out. So we have the 10 meters, and then multiplied by the area, which is pi r squared. What is the radius here? The radius here is 2. 4 divided by 2, 2. So we're going to get 4 pi. And gamma is 9.8 kilonewtons per cubic meter. So 9,800 multiplied by 10, 98,000 multiplied by 4 is going to be 1.23 meganewtons. So the force that is being applied, the hydrostatic force, the force that is due to hydrostatic pressure, right, is equals to 1.23 meganewtons. But where is that force is being applied? We are looking for y of r and y of c, and x of r, sorry. So y of r, we have the equation. It is going to be I x of c divided by y of ca plus y of c. Y of c here is 10 divided by sine of 60. What is sine of 60? 60 degrees, does anyone remember from mathematics? What is sine of 30? 30 degrees. Wasn't it 1/2? Doesn't ring a bell? Sure? Okay. Sine of 60 was a square root of 3/2. Well, I guess you can use a calculator for it. And you plug the values in, you'll find the y of c. Then we need to find I x of c. We have the formula again. It is pi r to the 4th divided by 4. Just have to keep in mind that r here is the radius. So I x of c is pi 2 to the power 4 divided by 4. Plug this value in here. We can calculate y of c using this number, and we have already calculated the area, 4 pi. Plug all of those values in. Y of r is going to be equal to 11.6 meters. So this force is being applied to a point that is 11.6 meters deep. What about x of c, x of r? We need to have I of x, y of c. If you look at this formulation here, I of x, y of c is 0. And then we have to add it to, let me actually write the formula just to make sure we are all on the same page. So x of r is going to be equal to I x y of c divided by y of ca plus x of c. X of c here is 0 because we are not given any information on it. We are just going to assume x of c is 0. R of xy of c is 0 as well based on that. So x of r is 0. So the point that force is being applied on is 0 and 11.6 meters. The only thing that you have to make sure you are keeping in mind is that this is going to be our coordinate system. So y is positive in this direction. So when I say 11.6 meters positive, it means that 11.6 meters deep. Okay, so this force is being applied on a location that is deeper than your centroid. Okay, so essentially this force is pushing your gate in this direction, right? It wants to rotate the gate counterclockwise. That's why we have the stop. Is there any questions? Let's continue the discussion then to talk about the next topics. The next topic is going to be pressure prisms. Yeah. When it comes to finding the force, total force on a point on a gate or whatever that is, we can use another methodology which is called the pressure prism. Okay, let's look at that wall again. The idea was if this is your free surface, it will have this type of pressure distribution. Yeah, in this dimension. Total force that is being applied here is going to be equal to the average of this pressure multiplied by the area. That's another way of looking at it, which is going to be, in this specific case, average of pressure, because we have a linear distribution, the average pressure is essentially applied here. So it is going to be equal to gamma h over 2 divided by, let's say the height here is h, multiplied by a. And if it's a rectangle, your a, let's say it is b, the length in this direction is going to be b, you're going to have hb. Okay, so we eventually going to have 1/2 gamma hb. And we have two h's. Gamma h. So what is this? What is this? What does it give? What does this value give? Gamma h, h multiplied by b 1/2. Let's look at this pressure distribution. So on one side we have gamma h, on one side we have h, on one side we have b. Okay? This is essentially a multiplication of these three sides, the width, length, and depth of it. This is essentially going to give us the volume of this whole thing. And this is a prism, so the volume of this prism is essentially 1/2 of that value. So your resultant force, from another perspective, is a volume of this pressure prism. Again, it's the same idea, it's the same, it has the same objective, but it's a different perspective. And it's going to be beneficial in some specific type of analysis that's going to make our lives much, much easier. So let's look at this type of situation. Let's say we want to find the total force. Again, let's go back to this wall, free surface. Let's say we want to find the total force that is being applied on this part of the wall, specifically on this part of the wall. And here is the pressure distribution here is going to look like this. But we are only interested in the resultant force on this part of the wall, right? Nothing else. That's the only part we are interested in. So we are going to take this. And we are going to divide this into two parts. Let me remove all of the other parts. Two parts, part 1, part 2. And then you calculate the volume of this part 1 and then part 2. Add the two volumes, you're going to have your resultant force. So essentially F of R is going to be equal to F1, F2, or volume 1 plus volume 2. Okay? How do we calculate the volume of this part? Pretty easy. Let's say this height is H1. The idea is pressure here is gamma H1, right? So we have this length, this size, gamma H1, right? And this is usually should be given to us, B, right? And then this is height H2, which should be part of the H1, H2. This should be given to us, right? They are going to tell us that find the pressure between these two depths, right? The total pressure. So we have this side as well, H2 minus H1. Sorry. H2 minus H1. So the volume of the part 1 is going to be H2 minus H1 multiplied by B multiplied by gamma H1, right? One side is gamma H1, one side is B, and one side is H2 minus H1. So that's volume of the whole cube. Then plus the volume of the next part, the prism part, which is going to be 1/2 this length. This length is gamma H2 minus H1, right? So this pressure here is gamma H2. We have to remove this length from it, which is gamma H1. So eventually you'll end up, for this length, you'll end up with gamma H2 minus H1. Does this make sense? Yes? So gamma H2 minus H1 multiplied by B multiplied by gonna be again H2 minus H1, which is going to be the depth of it, right? H and the depth. So calculating the volume made by this pressure distribution and adding them up is going to give you the total resultant force here. And using this methodology, you don't really need to do any, I don't want to say you don't need to, but in the as long as you have the length here, this length, you won't really need to do any like sine and cosine or use any moment of inertia or anything like that. Unless you want to find the location, of course. But for the forces themselves, just find the volumes, and you should be good to go. Let's solve an example here. And then we are going to move forward. So in this example, we have a container that contains oil. So oil and air on top of it. Oil is connected to a pressure gauge. This pressure gauge is showing P equals to 50 kilopascal. Then we have a small door, if you will, here that we use to let the oil on. It is located 2 meters beneath the free surface. It is 0.6 meters deep itself, 0.6 meters, so 60 centimeters. It is bolted, the plate is bolted at all sides. So we have these bolts here. So it is fixed in place. Okay. The outside tank is at the atmospheric pressure. We want to find the magnitude and location of the resultant force on this attached plate. So let's take a look at this from a side. Let's have a side view on this. This is a side view of this plate. The pressure force, the hydrostatic pressure force, is going to look like this. So you are not going to start from 0 because you are not at the zero depth, right? You are going to start from some value. So some part of it is going to be part of the prism. We are going to have essentially 3 contributions to the hydrostatic pressure here. One is going to be air pressure, which is always 50 kilopascal. This is what the thing is reading, right? Here, in this case, or in most cases, the container is open to the atmospheric air, which we assume from a gauge pressure point of view, the atmospheric pressure is 0, right? But this is not open to atmospheric pressure. So whatever you calculate, you have to add the contribution of this pressure on top here to it, right? So in this problem, it will be volume 1 plus volume 2 plus the contribution of that air that is located on top, which is also another volume, right? It is going to be 50 multiplied by d multiplied by this height. Does this make sense? No? Yes? No? Yeah, we had one no. Okay. So let's forget about the gauge pressure for a second. Let's solve this without the gauge pressure. If you look at it from the perspective we had from here, we essentially have 2 volumes we have to calculate. One is going to be your gamma of oil H1, right? This is going to be this depth, 2 meters. So 2 gamma, and then the plate itself is 6 meters by 6 meters, right? So 6 meters, 6 meters. Like the volume of this whole thing is going to be 6.6 meters. 0.6 multiplied by 0.6 multiplied by 2 gamma of oil. Are we clear up until this point? Okay. And for the prism, this part is gamma depth of this location minus the depth of this location, H2 minus H1, which is going to be 2.6 minus 2. So 0.6 gamma here, and the rest of the length is 0.6, 0.6. So that's the same. So volume 1 is going to be 2 gamma of oil multiplied by 0.6 multiplied by 0.6 plus the volume of the prism you have. What is the volume of the prism? It is going to be 1/2 0.6 gamma multiplied by 0.6 multiplied by 0.6. This would have been the hydrostatic pressure if the container was not sealed, if it was open to the atmospheric pressure, right? When it's not open to the atmospheric pressure, you are adding extra pressure at this location that is due to the presence of this air on top. That extra pressure is always the air pressure. That doesn't change. This is not a hydrostatic pressure, right? This is not the hydrostatic pressure we are interested in. That's 50 kilopascal. And to find the resultant force, we just have to convert that 50 kilopascal to force. Essentially, we have to multiply it by the area of the plate, right? So, plus 50 multiplied by 0.6. That's actually 50 kilopascals. So 50 to the power 10 to the power 3. Plus, so it is essentially the same as thinking of this pressure as another volume 3 with uniform pressure distribution. So 50 at each location. Does this make sense? Okay. And to find the location that is being applied on, you essentially have to separate these two volumes, multiply them by their own y of r, if you will, which is going to be y1 and y2, and then write the moment balance again. So fr multiplied by, let's call it y of r, f1 multiplied by y of 1, f2 multiplied by y of 2, has to be equal. We rearrange this equation to find the location this resultant force is being applied on. How do you find y1 and y2? Using the equations that we already had. It was a function of moment of inertia, the center of its location, and all of those nice things. But we're going to solve some examples with this, so hopefully it is, if it's not clear for you, hopefully it will become clearer on Tuesday. So the next part is the hydrostatic force on a curved surface. Let me actually bring this part. Hydrostatic force on a curved surface. Let's say you have this curved surface that starts from here, and we want to find the hydrostatic force on this curved surface. The only thing that is going to make this different than the other cases is that the force, hydrostatic force on this curved surface is going to have two components, right? One is going to be called F of H, and the other one is going to be called F of V, right? We are going to, essentially your analysis, your pressure distribution is going to look like this, and it's going to increase as you increase the depth, of course. So it will look like this. You have to have the pressure distribution, you have to find the components in each direction, and then find the resultant force. The direction is this direction, as Fh to the power 2 plus Fv to the power 2. I will make sure that we are gonna solve an example with this, but the physics of it is just that. You just have to find the components of the force, and then find the total force using this thing that you have seen before. Sometimes the questions are from these type of problems, the curved surfaces become a little tricky. So I will make sure to solve an example definitely from this part during the next lecture. But if you had any problems, you have to make sure to talk to me and ask your questions. Is there any questions? No? Let's actually do this. Let's talk about buoyancy. Who can tell me, or what is buoyancy? You have heard the word, yes?
Isn't it just volume of displaced water or something like that?
That's it. That's it. So to calculate, thank you. To calculate buoyancy, but let's back up a little bit. Let's see what buoyancy is by itself. Buoyancy is the force your fluid is going to exert on a submerged object or a half submerged object, right? So whatever that is submerged in a liquid, a pool of liquid, or in air is a fluid by itself, right? Like a balloon or whatever, right? Is that fluid is exerting a force on it, right? And that force is called the buoyancy force. Well, how can we calculate buoyancy force? As your, what was your name again? Connor. As Connor mentioned, we essentially have to find the volume of that object, right? Let's say this is a submerged object. Find the volume of that object, whatever that is, and multiply that volume by the gamma of that liquid or fluid, whatever that is. So your buoyancy force is going to be gamma of that replaced fluid. Replaced fluid multiplied by the volume. Okay. So what does it mean? Let's say we are trying to submerge an object that is made out of foam, and an object that is made out of steel, which one is going to face higher force? Or which one will be pushed back more? Is it the same volume, everything is the same except for the objects, except for the material. So the shape is the same. We have a ball of steel, we have a ball of foam. And we want to submerge them in a pool of water. Yes?
The foam.
The foam. So, what's your name?
Connor? Also.
Connor, Connor. Okay. Yeah, I remember you too, yeah. So Connor is telling us the foam is going to face a higher buoyancy force, right? But let's look at the formulation here. And that is the assumption most people make. So I assume anyone else would have given me the same answer, right? But let's look at the formulation we have. Let's look at the formula, the definition of buoyancy force. It's the gamma, the specific weight, or the density multiplied by the gravitational force of the replaced fluid, right? It doesn't say of the object, of the replaced fluid. The fluid hasn't changed, it is water. So why would the buoyancy force change, right? So based on the definition of the buoyancy force that is going to be felt by the object that is being submerged is going to be the same as long as the volume is the same, right? It doesn't really matter what the material is. The total force, though, is a different thing, right? Because when you're dealing with foam, you probably are dealing with a lower weight object if it's the same volume. So the foam, the buoyancy is going to be more dominant, and the foam will probably float, right? But the ball of steel will probably won't float. So it can overcome the buoyancy because of its weight, right? But the buoyancy force is not a function of the material you're using, or even the shell. As long as the volume is the same, your buoyancy force has to be the same. Okay, so let's solve an example here. Yeah, let's solve an example here. This is also a book example, and it is telling us that a type 1 offshore life jacket of the type worn by commercial fishermen is shown in the picture. We don't need the picture. It is designed for extended survival. It's just explained. Extended survival in rough, open waters. According to U.S. Coast Guard regulation, the life jacket must provide a minimum 22 pounds net upward force on the user. So I'm just gonna call it FN. The net upward force, it has to be 22 pounds. Okay? And let's say this is a person, or this is a life jacket. Very badly drawn life jacket. Person. So the net force that is being exerted on this has to be 22 pounds. Net force, total force, okay? And consider such a life jacket that uses a foam material with a specific weight of 2 pounds per square feet. So gamma of this foam is 2 pounds per cubic feet. Instead of square feet. Cubic feet. For the main flotation material, the remaining material, the clothes, the straps, the fasteners weigh higher than 1.3 pounds. So weight of the rest, just gonna call it W, is going to be 1.3 pounds. And the volume of the whole thing is negligible. Okay. We want to find the volume of this rest of the material. We want to find the volume of the foam needed for this life jacket. So what are the forces that are present here? One is the weight of the foam, that is pushing it down, W of F. One is weight of the rest of the material, W. What other force do we have here? We have the buoyancy force, right, that is pushing it upward. Okay, and it is in water. So essentially, you have to write the force balance here. The buoyancy force plus your 22 pounds is actually 22 pounds or minus 22 pounds. 22 pounds have to be on the other side of the equation, right? Because your resultant force has to be positive 22 pounds. So gamma of foam multiplied by the volume of the foam plus 1.3 pounds plus 22. Okay, so what is the buoyancy force? It is gamma of water in this case. And you probably recall that gamma of water is 62.4 pounds per cubic feet in the SI system, multiplied by the volume of the foam is equals to gamma of foam, volume of the foam plus 1.3 plus 22. Okay, we have gamma of the foam, we have gamma of the water. The only thing that we don't have is going to be the volume of the foam, which we can easily find, right? And you will eventually find the volume of the foam to be 0.376 cubic feet. So this life jacket can float someone who weighs 22 pounds, which is essentially a baby. Is there any questions about the buoyancy force? Yes.
What did you say the final answer was that we get for it?
0.376. The next thing we want to talk about is the stability, which is one of the results of this buoyancy force. Okay, let's say an object is submerged in water. You have the free surface. You have an object like this that is merged. What is going to happen if you try to push the object in this direction? It is submerged underwater. What is going to happen to it if you try to apply a couple or a force in this direction? Will it rotate or will it go back to its original position? So it will go back to the original position. You said it or you wanna, yeah, the other column, okay. It can, it depends. But what does it depend on? It depends on the location of center of gravity and the location that this buoyancy force is being applied on. Buoyancy force is applied on the centroid. And the weight, we only have weight and the buoyancy force here, right? Is applied on the center of gravity. Let's say you have your centroid here, and your center of gravity here, which means that you are going to have a force, weight force being applied here, and FB applied here. Let's say I push this star to the left, the other is here. It will look something like this. Okay? This type of force is going to generate a couple in this direction. Okay? So if I try to push this object to the left, there will be a restoring couple, something called a restoring couple. That will force the object to its original location. Do we see that? We will have this type of couple, right? The same thing would have happened if I push the object to the right. We would have a restoring couple in this direction, right? Well, what will happen if our centroid and center of gravity are replaced? So we have center of gravity here and centroid here. A buoyancy force and gravitational force. If I push this to the left, you're going to get weight, you're going to get buoyancy force. So there will be a couple in this that will force it to move further. Does this make sense? So it all depends on the location of center of gravity and centroids. This case, this object is called a stable object because small disturbances won't really affect its location. If it moves to the, if it rotates to the right or left a little bit, it will go back to its original location. But this one, this other submerged object is called unstable because if you move this object to the right or the left, it will move further. But an interesting phenomenon that is not mentioned in your book, but I guess you can think about it. What will happen if the centroid and center of gravity are the same location? So weight and F of B are being applied to the same location. What will happen if I rotate this to the right a little bit? Will there be a restoring couple or will there be an overturning couple? Overturning couple. What do you think? You want to say something? No one? Just think about it. The couple, to have a couple, we need to have an arm. The forces have to be distant. What is the distance between the two forces here? 0. Exactly. Don't know who said it, but whoever said it, 0. That's correct. So there won't be any couple generated because of the small rotation to the right or the left. What does it mean? It means that if I rotate this object to the left, it will stay at location if there's no other disturbances or forces, right? It will stay at location. And this is called a neutral condition. Whenever you want to understand this better, think about a ball. on a surface. If you have this type of surface, a ball here, if you move the ball to this direction or this direction, it will go back to its original place, right? If you have this type of surface, which is the unstable surface, if you move the ball to any direction, it will move further. It will go down. And a neutral surface is this type of surface. If you move the ball in this location, it will stay at its new location. So stable, unstable, neutral. And all goes, this stability for a submerged object all goes back to the buoyancy force. We should go ahead and start the next part, or should we wait? There is actually an online question. Is that y r equal to the integral of y squared dA? That was f of r equal to f of r multiplied by y. If you are still here and have a question. Okay. I guess we can at least start the discussion. It's going to take a long time. So the next part of the lecture, which I'm not going to talk about here, I'm just going to explain it a little bit, and then we'll focus on it more on the next lecture. There are only two other subjects that remains in this chapter, and those are the cases, the pressure variation with motion. It's called the rigid body motion. So the container of the fluid is moving, not the fluid itself. The movement of container is going to cause some movement in the fluid, but there is no fluid velocity, if you will. There is no pressure difference that is going to cause the fluid to move inside the pipe or whatever. The container of the fluid, of the liquid, or a sealed container of the gas, I think that is moving or rotating. This is something that we are going to focus on in the next lecture. And this will conclude the fluid statics. But essentially, to analyze that type of movement, you have to go back to the general hydrostatic equation we had, which was the changes in pressure minus gamma K was equals to sigma F equals to MA. So we have changes in pressure as one force. We have the weight force as another force, gamma, whatever, specific weight. MA, we will have an acceleration here because the fluid tank is moving. It's called the rigid body motion. And so the rho A part is not going to be 0. So let's think of this as a starting point, and then we'll focus on this. I will cover these two parts quickly on Tuesday. Then we'll go to solving example problems, 3 or 4 example problems. If there is part of the fluid statics chapter 2 of the book that you don't really understand, send me an email. I'll try to make sure that we solve an example that covers those parts as well. Okay. If you haven't submitted your homework, make sure you do so. And that's it for today. Have a good weekend. Let me know if you have any questions. And